Welcome to this calculus video on continuity and differentiability. We've looked at continuity already at this point in the course when we were dealing with limits. Now what I'd like to do is I'd like to kind of review that concept just briefly and then extend it further. Now that we know all about the derivative and we know how to take most derivatives, I want to talk about this idea of differentiability, which is kind of like continuity, but it's related to the derivative. It's to answer the question, where does a derivative exist for a function? All right, but before we go into differentiability, let's start with a recap of continuity. So recall this definition of continuity. This is working through the notes that you have in your calc binder. We're starting at page 70. So this definition is there already. You already should have it in your notes. It should be a flashcard. It should be something that you already pretty much know at this point. So just a quick reminder. A function's continuous at a point C if three things are true at that point. F of c exists, so the function has a value. The limit as x approaches c of the function exists, which means as you get closer and closer to c from both the left and the right, you approach some value. And then the third condition is that value that you approach has to be f of c. Okay, if that happens for every value of x in your domain, then we call the function a continuous function. If that doesn't hold for a certain point, then we would say there's a discontinuity at that point. Okay, let's look at some continuity graphically, just as a reminder, and looking at what rules are failing for the ones that are not continuous here. So we can do this rather quickly. So graph A at 1, you can see that it's not continuous. You know, we can still use that intuitive nature that graphing something without picking up your pencil is what it means to be continuous. But now that we're in calculus, we want to be more sophisticated about how that definition breaks down. So for graph A, this is not continuous at 1. And the reason why is because the limit as x approaches 1 does not exist. Notice that from the left of 1, we're getting closer to this hole, but from the right, we're getting closer to f of 1. So since the limit does not exist, we can't be continuous there. Part B, graph B, is also not continuous at 1 for a different reason. F of 1 does not exist because we have a hole at 1. From the left of 1 and from the right of 1, we do get closer and closer to some value, but that value is not f of 1. So the limit does exist here, but it doesn't equal f of 1. Now at graph C, as we get closer and closer to both sides of 0, we do approach f of 0, so this one would be a continuous function at 0. D would be the same thing. From both sides of 0, we get closer and closer to f of 0. Now, little preview for the next second half of the video. This function's not differentiable at 0. More to come on that in a few minutes. You could probably do the rest of these on your own, E, F, G, and H, and just to be a good exercise to think about what parts of the definitions break down. They're basically going to be discontinuous, except look at G, be very careful. They want it at -2, and at -2 we're okay. Just because there's a hole in one spot doesn't mean the function isn't continuous elsewhere. So actually for G, that is going to be a continuous function at the point they give you, -2. At, let's say, maybe this is +1, no. But at -2, certainly. Also recall some of the types of discontinuities we looked at earlier this year. So remember in graph A, we would call x equals 1 a step or a jump discontinuity because the limit from either side of 1 doesn't match up. In B, we would call that a removable discontinuity because at x equals 1, we have a hole, so the limit exists, but it doesn't equal the function. And if you want another visual example, at graph E, we would call this an infinite discontinuity because either side of 2, the graph goes off to either positive or negative infinity. This is a vertical asymptote case. Okay, so that's just some review of continuity using graphs. Let's also talk about continuity algebraically or analytically, because you might be given a function and be asked, okay, is the function continuous? If it's not, well, where is it not continuous? And so on and so forth. So this box, and this box is on page 71 of your notes, is actually a pretty handy one. We talked about continuity before, but this gives you a nice idea of some conclusions about specific types of functions and specific classes of functions. And most of these we did talk about already, so I'm just going to briefly go over them quickly. Recall that we said earlier when we were discussing limits, any polynomial has to be a continuous function. That's why we never really worried about continuity in our earlier math courses, because most of the functions we dealt with were polynomials. If you have a fraction, a rational function, you're going to have a discontinuity whenever your denominator is 0, so whenever g of x is 0, because you'll have an undefined function value, because you'll have a number over 0. Now, it's as important. It doesn't matter whether or not you can cancel out a factor. It'll still be discontinuous. The difference is, when you can cancel something out, the type of discontinuity is a removable discontinuity as opposed to a vertical asymptote. Okay, radicals. Depends on the index of the radical. If you have an odd root, we don't have to worry so much about continuity. It's going to be continuous everywhere. And that's because it doesn't matter whether f of x is positive, negative, or 0. You can take a cube root or a fifth root of that value. Now, if the radical is an even root, the square root of x, the fourth root of x, the 10th root of x, that's going to be discontinuous, or discontinuous, excuse me, wherever the function is negative, because you can't take an even root of a negative number. And then the last two classes of functions are easy to work with. Trigs, at least sine and cosine trigs, are going to be continuous everywhere. Remember, when we start dealing with our ratios and our reciprocal functions, tangent, cotangent, and whatnot, we will have some discontinuity issues because we'll have some vertical asymptotes. Exponentials are also going to be continuous everywhere, and that doesn't matter whether the base is a number like a or the number e. It will always be continuous, okay? So I have a nice set here of some functions, and they ask us to find points of discontinuity. And again, we can kind of go through these. I'll do some, and then I'll let you try to fill in the rest. So graph A is a nice polynomial, so there's no discontinuities. There's not a point of discontinuity in this one. Or in other words, this is a continuous function. Graph B, we have a fraction, x squared minus 1 over x minus 1. Now, like it says up in the table in part B, we only care about when is the denominator 0, and that's going to happen when x equals 1. So this graph will not be continuous at 1. But note something, that f of x can be factored and canceled as x minus 1 over x plus 1 up top, and then the x minus 1 on the bottom. So since we can cancel out that x minus 1 factor that made the bottom 0, it's still not going to be continuous at 1, but we can be a little bit more specific, and we can say that that discontinuity is going to be removable. There'll be a hole at 1. And in fact, this graph will graph just like the line y equals x plus 1, except there will be a hole at 1, too. Okay, C, we have a root, but it's an odd root, so this one's going to be continuous everywhere. There's no issues with negative roots for cube roots, so there's no points of discontinuity. You could take a look at D, E, and F, same kinds of ideas. Just be careful with D. You want to make sure, since this is a square root, that the radicand, x squared minus x minus 6, has to be positive, so you're going to have to do some work with quadratic inequalities. Which I know you've done before in Algebra 2 and Pre-Calc. You're going to use a number line and figure out what interval would make this negative, because in that interval of values, this graph will not be continuous. Now, a second type of algebraic problem involving continuity is usually piecewise functions. So usually when you deal with a piecewise function, especially the piecewise functions they'll give you on the AP exam, each piece itself is typically a continuous function. And in fact, for most of these, especially 3 and 4, we're dealing with polynomials. Each of them separately would be continuous. The issue is where the function changes rule. So at that breaking point, we need to check and see is there continuity. So essentially what we do is we're going to plug that value of x into both pieces and see if the pieces line up. So we'll try number 3 together. So first we'll look at the limit as x approaches 1 from the left. and that means we're looking at values of x less than 1. So we're going to plug in 1 for x squared minus 3, and we get negative 2. We'll do the same thing when we approach 1 from the right. So now we're going to plug into the bottom function. Okay, well, we get 1 minus 1, we get 0. So this means the limit as x approaches 1 of this function does not exist. So f is not continuous at 1. Okay, so even though it's made up of two continuous functions, there's a gap at 1. There's going to be a jump discontinuity because they're approaching different values from either side of 1. Let's look at number 4. So we'll do the same thing, except the rule here changes at negative 2. So let's check the limit as x approaches negative 2 from the left of f of x. That means we're going to put negative 2 into the top function. So negative 2 squared plus 3 times negative 2 minus 2 will get me 4 minus 6 minus 2, and that would be negative 4. And if we do the same thing as we approach negative 2 from the other side, and use the negative x squared rule, we get negative quantity negative 2 squared. It's also negative 4. So this one is good. F is continuous at x equals negative 2. So this will be a nice continuous function. When the rule changes, the two pieces will match up. Again, we've done a bunch of these before. I'm not going to waste your time and do these with you. You can try 5 and 6 on your own. Again, you're just kind of checking at the break-off point and see what goes on from there. The other important question, just to remind you of where we've been, is what if we have a variable in our piecewise function, some sort of parameter k or a or whatever letter they decide to use. They want you to basically come up with the value that's going to make these line up at the rule change. So you're going to do the same idea, except you're not going to get a numeric limit for both pieces. You're going to have some sort of expression for one or both pieces that you'll set equal to each other to make the function continuous. So if we look at part A, we'll do the limit as x approaches, okay, what's the break-off point? 1. We'll do it from the left of f of x. So the rule I'm going to use there is 3x plus 2. So that limit is 5. So in order to make f continuous at 1, the limit from the right has to also equal 5. So let's see, based on what they gave us, what the limit from the right looks like. Okay, we'll put in 1 for x, so we have 2k minus 1, and that's as far as I can go. 2k minus 1. So now I'm going to take these two limits and set them equal to each other. Bring the 1 to the left. K is 3. So if we put a 3 in place of this k, these two pieces would line up. Okay. Again, you can try B and C. We've done problems like these before. You can see them and do them for yourself. The difference for B and C is you're going to have k's in both limits, so you'll have to do a little bit more algebra. In C, you'll have a quadratic, so there'll actually be two values of k that would make that piecewise function continuous. So that's kind of where we've been with continuity, a very quick review of continuity, making functions continuous, what it means from a limit standpoint. Now I want to bring the idea of a derivative into this and talk about differentiability. So now what we're talking about is that a function would be called differentiable at a point if it has a derivative at that point, if the derivative is defined to be something at that point. And if that's true for the entire domain, then we can say that the function is a differentiable function. In other words, you can take the derivative of that function. All right, and on page 72 in the middle in the box, there's some 3 separate definitions about differentiability. They kind of just go from the most specific to the most general. So at a point, we can talk about differentiability. If can you take the derivative at that specific value? You can talk about differentiability on an interval, which means if every value within a given interval has a derivative, then we can say the function's differentiable on that interval. And then most importantly, if a derivative exists for every value in a domain, we call it a differentiable function. The good news is a lot of functions that we work with are going to be differentiable. Polynomials, the sine function, the cosine function, the exponential function. But you knew that already because you know how to take all those derivatives. The power rule, the trig rules, the e to the x rule that we've learned. We wouldn't be able to use those rules if those functions were not differentiable. Now, there's an interesting relationship between differentiability and continuity, and I told you we'd get to this relationship, because remember how we've looked at some sample AP problems, and in some of those sample FRQs and MC questions, they mentioned about a function being differentiable? A lot of times they won't go into the details of saying that a function is continuous. They'll just say a function's differentiable, and there's a reason for that. Differentiability implies continuity. So if you're told a function is differentiable, you can automatically assume it's continuous. Now, I wouldn't necessarily assume it, like without writing it on a free response question, but you can determine, if I tell you it's differentiable, something you can write down in your answer is you could say, well, I also know that f is continuous in the event you need continuity for something. Like, for instance, an intermediate value theorem problem. A lot of times you'll see those. Remember, for the intermediate value theorem, we had to prove continuity. Well, if they tell you a function's differentiable, then you can say, well, since you told me it's differentiable, I know it's continuous. All right? We'll talk a lot more about that relationship in class because it's important. Another thing we're going to talk a lot about in class, which is important, is the converse of that statement. So for those of you that have done some logic, especially those of you that are in HAMS, you know what a converse is. For those of you that don't know what a converse is, I'll tell you now. If you have an if-then statement, so if differentiable, then continuous, the converse would be taking the if and then and switching them. So if a function is continuous, then it is differentiable. That is not always going to be the case. It might be, but it's not always the case. What is true, and it's the third bullet in this table, or in this box, is the contrapositive. That will always be true, and that's a statement about logic, not just about this relationship between differentiability and continuity. And what that means is, the contrapositive, for those of you that don't know, is you switch your if and then, and you negate both the if and the then. So if we're not continuous, then it's true that we are not differentiable at a point. So that's kind of cool too. If you know something's not continuous at a certain point, you get that for free, that it's not differentiable as well. All right, so that's the relationship between differentiability and continuity. That's why I wanted to review continuity in the first half of this video. Now, let's talk about graphically what it means when a derivative does not exist. Okay, we've already handled the points where a graph is not continuous. These are the other ones. So here's places where something can be continuous but not differentiable. Notice, and I picked these on purpose to continue that idea of the converse not necessarily being true. All continuous functions on your screen right now, but at x equals 0, none of them have a derivative. And let's explain why. So in the first picture, we have a corner. What we mean by that is, as you get closer and closer to 0 from the left side, notice how your tangent lines from this side are negative, because this graph is decreasing towards 0. Notice on this other side, the tangent lines are positive from the right. Well, then which is the slope at 0? Is it a negative line or is it a positive tangent line? Since I can't draw two tangents at one point, I can't say that this graph has a derivative at 0. Okay? Second place that can happen is a cusp. So same idea. From the left and from the right, the tangent lines have different slopes. So at 0, there's not a limiting value for that slope. So we can say the derivative does not exist. Finally, in the third graph, at 0, the tangent line is a vertical line. We know vertical lines, the slope does not exist. If the derivative is the slope of a tangent line, and at 0, we have a line whose tangent has a non-existent slope or an undefined slope, the derivative can't be defined at that point. Okay? Basically, visually, you'll know when you see it, because a point that's not what we call a smooth point is going to be one where we're not differentiable. Notice, like I said, there's a corner, something jagged, a corner, a cusp, a vertical tangent. That's the graphical representations of these. But again, we have to understand these things from all different dimensions. So let's talk about checking them algebraically. Okay, so if you're given a function, particularly a piecewise function, and you're asked to check whether or not it's differentiable, what you're going to do, First, you're going to check continuity, because remember, if it's not continuous, it's not even worth me checking differentiability because of that contrapositive idea. Second thing you're going to do, if it is continuous, you're going to take the derivatives of each piece of the piecewise function and check and see if they match up. So in other words, you're checking, is the derivative continuous? That's what you're basically checking when you're dealing with a piecewise function. All right, so let's do some examples of that. Okay, so the first one we have f of x equals x squared minus 6x plus 10 when x is less than or equal to 2, and 4 minus x at x is greater than 2. All right, so we'll start with continuity. So we'll do the limit as x approaches 2 from the left. I'll plug into the top piece. I get 4 minus 8 plus 10. Or sorry, not 8, 4 minus 12 plus 10, and that gets me 2. I'll try it again from the right. That's 4 minus 2, that is 2. Okay, so the limit as x approaches 2 from either side matches up, so f is certainly continuous. Now let's check the derivative. So we'll take the derivative of each piece. So that means from the left, our derivative is 2x minus 6. From the right, it's negative 1. Okay, and I'm just using the power rule on each of these because they're nice polynomials. So let's look at the limit as x approaches 2 from the left of the derivative of f. Well, when I make x 2, I get 4 minus 6. That's negative 2. We have a problem, though, because from the right, we approach negative 1, because every value bigger than 2 has slope negative 1. So that means this function is not differentiable at x equals 2. All right, and I will look at the graphs of these in a few moments. I'm going to do the work first, and then I'll show you the graphs on my Inspire. But you'll visually see what's going on at x equals 2 here, why it's not differentiable. Let's do the same thing with graph b, or function b. So now our breakoff point is at negative 1, and this is actually a typo. There should be a comma here in this second piece. This is just negative x minus 4 when x is greater than negative 1. So we'll try the limit as x approaches negative 1 of the original function. That's going to be negative 3. You can check me on my arithmetic. We'll do the same thing from the right, and we'll use the bottom piece. That's also going to be negative 3. So we're good. We know f is continuous. Now we're going to do differentiability. So we've got to take the derivative of each piece. All right, for x is less than or equal to negative 1, the derivative is 2x plus 1. And for x is greater than negative 1, the derivative is negative 1. So we really just have to check and make sure, since we have another constant from the right, we just really have to check if the limit as x approaches negative 1 from the left of the derivative equals negative 1, and it indeed does. So f is differentiable at x equals negative 1. Okay, and I can show you on the graph why a is not differentiable and b is. So now if I put up my graph of these two functions, so this is the first function, this was 8a, and we established that this is continuous, but it's not differentiable, and it might be hard to see right here on your window, but if I take my zoom, and I take a zoom box, and I go really close to x equals 2, notice how it gets kind of jagged here at 2. Move the label away. Notice that as you walk along this curve, you kind of hit a corner here at x equals 2. That shows you that while this function's continuous at 2, it's not differentiable. You can't really discern what the tangent line looks like. You know, is it going to be drawn like this? Is it going to be drawn more like that? How could you do it? How could you draw a unique tangent line at that point? Let's compare that to the graph of function b, and here that is in red. Again, it is continuous, but now if I go and zoom closer and closer to x equals negative 1, you'll see that it's not a jagged corner, but rather it's a nice smooth curve that's happening here. Okay, so you can still take a derivative, you can still draw a tangent line at x equals -1. So we are differentiable and continuous here. Now the final piece of the puzzle is kind of like we did with continuity. If we have some parameters, we have some additional variables in a piecewise, how can we make the function differentiable? So this is kind of a 2 for the price of 1 sort of thing. We're going to have to play the same continuity game we've played, and we're also going to have to play the differentiable game of making sure those limits line up. So we'll start with continuity. So that's the first step. I'll do 9a only, and then you can try b on your own. So step 1 is we've got to make f continuous at x equals 1. So we'll start by taking our limits from either side of 1. So when I plug in 1, I'm going to get a plus 1. When I plug in the limit as x approaches 1 from the right, I am going to get b minus 3. So that means a plus 1 has to equal b minus 3. You might be thinking, okay, I don't have enough information to figure out a and b, and that would be true. So what we have to do next is we've got to consider differentiability. We've got to make f differentiable as well at x equals 1. So let's look at the derivative of the piecewise function we were given. So for the top piece, the less than 1 piece, our derivative is 2ax. For the bottom piece, the derivative is b. So now let's take the limit of either side of 1 for this function. So as we approach 1 from the left of this derivative, we get 2a, and the limit as x approaches 1 from the right of the derivative would be b. So to be differentiable, 2a has to equal b. So now I see why they gave us 2 variables, because we have 2 equations with 2 unknowns. So we'll solve the system. 2a equals b. I think substitution might be the easiest way to do this. So that means a plus 1 is going to equal 2a minus 3. So I believe with some algebra, 4 will equal a. Go back into this equation, 8 would have to equal b. So if 4 is a and 8 is b, this function would be a differentiable function. It would be continuous everywhere, and it would be differentiable everywhere. Okay? Do the same idea with 9b at some point, just for you to practice the mechanics of it. But that's really all there is to continuity and differentiability. The 2 big things you have to understand. Differentiability implies continuity. You have to understand visually on a graph, can you pick out points where a function is not differentiable? And again, it's going to be a corner, a cusp, a vertical tangency, or a point of discontinuity. And I guess a third thing would be using piecewise functions to check continuity and differentiability. Okay? If you've got those things down, you've pretty much mastered what you need to know about continuity and differentiability. We'll do a lot more examples and practice and exploration in class with this idea. Thank you for watching the video, and I will see you in class.